Yeah, let's continue our module 5, and here we can see more examples of our counter design. So here is another example where you have actually inputs to your counter design. So as you can see that we want to implement an up-down counter. So whenever the value of u is, let's say, equal to 5, sorry, 1, and then basically what happens is you have the counter counting upwards, which is from 0 to 1, 2, and so on. And whenever the value of d is equal to 1, which is for basically down, so the counter goes in the reverse direction. So from 0, 0, 0, it goes to 1, 1, 1, and then goes around. So in this case, so therefore we need an input that basically tells you whether you want to count up or count down. Another way to implement this is you do not need two variables to do it. We could have actually used one variable. So let's say a variable called input variable called x. So whenever x is equal to 0, then it actually counts up. And when x is equal to 1, then basically it counts down. So we could also could have just got away with 1. But then again, the advantage of using these two variables is that whenever the u is equal to 0 and d is equal to 0, or when u is equal to 1 and d is equal to 1, then typically you can make the counter stop at a particular value. Whereas with this particular implementation, you cannot stop the counter at a particular value. It either counts up or counts down. So anyhow, so that's basically why we go for this two variables or two inputs. And so since this is also a 3-bit binary counter, so we still use those three state variables C, B, and A. And then we have our next state, which is given. So here, filling of the table becomes easy, as you can see, because I have the state transition graph. So I can say that it's going from 0, 0, 0 to my next state. When it's up at 0, 0, 1, then push 0, 0, 1 here, and then it goes to 0, 1, 0, and then 0, 1, 0 to 0, 1, 1, and so on, and then finally goes back to 0, 0, 0. So when it's actually down, when d is equal to 1, so you can see it goes the reverse direction, which is 0, 0 becomes 1, 1, and if it was 0, 0, 1, then becomes 0, 0, so this one changes. Okay, so now since we have this, now we are going to also create, because we are going to do a t flip-flop, then we need to create our t, which is going to be t of c, t of b, and t of a. And then we'll also have the same condition when u is equal to 1 and when d is equal to 1. So pretty much what will happen is your implementation will have a 5-variable k-map because you have your 3 of your state variables along with 2 of your inputs, so which is u and d. So it becomes a 5-variable k-map. And if we are actually using a D, in this case we're using a D flip-flop, not a T flip-flop. So therefore, if you use a D flip-flop, then you'll have D, C, D, B, and DA as your outputs that are feeding into the flip-flop. Or basically they are the inputs to your flip-flop. So once you, in our case, because we're using the D flip-flop, we can simply replace this by DC, DB, and DA, and try to evaluate our 5-variable k-map, and you can see that we get these expressions. And then once we get those expressions, we basically will need to implement those expressions. Again, these things are not necessary, your feedbacks are not necessary, just simply use those values. As you can see, this is for B dash, and this is for A dash, and so on. So this actually implements a binary up-down counter. So now we're going to see a series of a simple counter. So here you can see the counter state transition diagram, or the state diagram is specified here. So there is no particular kind of order in which this is going. So it actually goes from 0 0 0 to 1 0 0. So it is not a binary counter. As you can see, it doesn't follow any kind of a Hamming distance rule. So therefore it doesn't bring a Johnson's counter or any type thing. And also you see that sometimes there are multiple ones, so therefore it is also not a ring counter. So this is basically a very generic simple counter, and since it only has about 5 states, so you can actually call it as an arbitrary mod 5 counter, which is basically stands for modulo 5 or modulus 5 counter. So what do we do? There are a couple of things that you can do here, and this is part of your optimization. So here you can see that even though we have these 5 states, but for your K-map, you require also to have your table completely represented. So which means these states, which are 0 0 1, 1 0 1, 1 1 0, is part of your design. So if we want to optimize it, then you can assume that you really don't care about what your next state is. So therefore you can have your C plus, B plus, A plus, your next state variables as just simply don't cares. And if you're actually using your T flip-flop, so therefore you can see that the T flip-flop, whenever we use TC, TB, and TA, so because you have these don't cares, those will also be don't cares. And so you will end up getting a lot of don't cares in your K-map, and thereby you will have a minimal solution. So in this case, we have seen this. So basically what we're doing is we have, this is your state, which is that. So your next state is that, so it goes to the next state. And then from this state, which is 1 0 1, as you can see, it goes to 1 1 1. Then from 1 1 1, it goes to 1 0 1 0. And from 0 1 0, it goes to 0 1 1. And from 0 1 1, it goes to 0 0 0. That finishes the loop. So the rest of it is simply don't cares. So now we're going to actually now create TC, TB, and T of A. So basically what we do is we take this and this, look up here, 0 1, which would be this, and your output is going to be 1. So that's how we're going to construct that table. We've seen this in multiple examples before, so I'm just going to list your table here. So that's your table that is there. And now we are going to implement 3 different K-maps for each one of them. So that's your K-maps for each of your expressions, TA, TB, and TC. And we actually get these equations. So once you get these equations, we are going to make 3 flip-flops. These are standard. Make a clock. For those flip-flops, connect all the clocks together. Then you label these flip-flops as TC, C, C dash, TB, B, B dash, TA, A dash. And so these are the expressions that you got for TC. This is the expression you got for TB, and this is the expression you got for TA. And that's pretty much completes your design. So in some cases, instead of actually giving you the state transition graph, you could also be given the timing diagram. So once you're given the timing diagram, so you can see that here, this is where the dotted line says that that's when the transition on the flip-flop happens. So you're given the values of C, and so what actually happens is, so for this instance, you can see if this is your current state, then this will be your next state. So when you construct your state transition, so it'd be coming from 0 0 0, it goes to 1 0 0, and then from 1 0 0 it goes to 1 1 1, and then from 1 1 1 it goes to 0 1 0, and from that it goes to 0 1 1, and then back to 0 0 0. So this is the same thing as what we have seen, but except that giving it as a state transition graph or a state diagram, you are actually given it as a timing diagram. So it is also possible to derive the state transition graph from your timing diagrams for a flip-flop. So now we're going to see a sequence of the same example, which is a modulo 5 counter, and we are going to actually see how you can perform these using the D flip-flop, the SR flip-flop, and the JK flip-flop. So you're going to see the same example performed across all 4 types of flip-flops. So here we have, as you can see, this is our current state, this is our next state, and we have actually included don't cares. And so now you can see that since it's a D flip-flop, you can simply replace our next state with simply your flip-flop inputs DC, DB, and DA. And so once you have implemented it, replaced it, so now we have to have 3 K maps for these 3 columns, and then we can see that we are getting these 3 expressions or circuits. In some cases, you might be required to evaluate what is the area in terms of gate counts or in terms of transistor counts. So here in terms of gate counts, you can see that I have for this design I have 3 flip-flops, and you can specify that you have 4, and if you want to be more specific, you can say you have 2 input gates, or in some cases you can specify I have 3 2 input and 1 3 input gates. So if you are actually requested for a transistor count, so typically for a D flip-flop, you require about 12 transistors to implement that. And for the case of a simple 2 input non-inverted gate, so you need about 6 transistors to do it. So let's say if you need, or if your implementation includes an AND or a NOR gate, then you need only 4 transistors to implement that. So anyhow, so in this case we actually require 6 transistors to implement each one of them. So you have about 24 transistors in that case and 36 transistors in that case. So in effective you need about 60 transistors for this design. So here is another example. So in this example we are going to use the same problem, but we're now going to use the SR flip-flop. So here is your excitation table for the XOR flip-flop. So students are requested to memorize the excitation table and the excitation equations for all the 4 flip-flops. The SR flip-flop, specifically, it's much easier to actually use the excitation table rather than the excitation equation. So we have, this is our excitation table. So here you can see this is our state transition diagram. We have our current state and the next state, and now you can see that we are going to use the excitation table here. So when we have C and C plus is 0 1, so which is this, you can see that we need S of C, that is from here, is a 1, and R of C, which is this, is going to be a 0. Similarly, when you consider something like this is 0 and here B is 0 and B plus is 0, so we look this thing up, and then you can see for 0 0 S of B will be 0, but R of B will be X. So what actually will happen is not only these don't cares, but now your SR excitation table will also introduce a lot of don't cares. So therefore, whenever you try to implement something using SR, and then you will see also with respect to a JK flip-flop, you will see that your expressions are much compact, and in general they would lead to a fewer number of gates, or they will lead to fewer number of transistors. But the design process is a little bit complicated because now you have to look up into this excitation table. In the previous cases, it was a simple XOR function, or simply replacing this by the DC, DB, and DA. But in this case, you will actually need to spend more time. And then, as you can see, since each of these SR and JK flip-flops will have 2 inputs each and not 1 input, so even for a 3-bit counter, you will need to actually generate 6 K-maps. So the design process is complicated, but again, you would actually gain on the number of gates. So here is your expressions for the K-map and the respective expressions for your SR flip-flop. And here you can see is the exact same implementation, but it's actually using an SR flip-flop, so your gates are really small. So now here is another example, the same problem, and you can see now we want to use the JK flip-flop, so that becomes the excitation table for the JK flip-flop. So we're going to use that, and now the expression is the same. This is your excitation table. So always I would recommend that you write the excitation table next to your current and the next state table, and whenever you're trying to actually come up with these input table from the excitation table, so you can actually look it up here. So here again you can see that whenever I have 0, 1, and so this goes into this, so here J of C becomes 1 and K of C is nothing but X. Similarly, when you have 0, 0, you can see that is your condition 0, 0, 0x, so that becomes 0x, right? And so we will continue to filter this, but whenever you have a don't care, it basically all becomes a don't care. So here is your K-maps for your 6 of those inputs, and these are your expressions. And so now you can see here again you have even more simplified. Actually, the JK flip-flop, or the jump and the kill flip-flop, because you can see it introduces more don't cares than even SR flip-flop. So therefore the JK flip-flop in general will give you the best possible solution for your design, generally an FSM design. So in summary, we have seen about design of counters, and we have also considered the use of unused states. So we have just used as a don't care, and then you can see that we also seen implementing of counters using 4 types of flip-flops. One other thing before we wind up is I just want to give you this. So let's say, for example, we know that when we actually design this, even though we introduce don't cares here, we just are assuming that these conditions are never going to happen, because if this happens, all you're saying is you really don't care what your next state is. And so in this design, we are very specific that these things are not going to happen. But let's say if this happens, then what happens? So then you can see that you will actually be in a state which is 0, 0, 1, and we have no idea where it's going to lead to. So therefore, one other way of just making that your design is foolproof is to make sure that it goes to a known state, but then you will have to sacrifice on the number of the don't cares, and then thereby your solution will become a little bit complicated. But then again, if for some reason, or even due to a glitch, if you end up in one of these 3 states, you can say that you can go to 0, 0, 0, which is your default state. So now if I actually design the circuit using this, then your circuit or your counter design becomes foolproof. All right, so thank you.